EG-121 Highway Design and Surveying Video Lecture 1. So this is the video lecture that accompanies the lecture early this week on Introduction to Surveying and Introduction to Levelling. These video lectures are essential to watch, really. There will be material that is covered in these videos that will not be covered in the lectures, and likewise there will be material covered in the lectures that is not covered in the videos. You need to be attending both the lectures and watching these to get all the course material. The reason being, you've only got one lecture a week, and that's not really enough to cover all we need to cover. So this one we're looking at levelling in a bit more detail than we did before. We'll look at using intermediate stations and get some practice booking level readings and performing level calculations. So in this video, I'm going to review the height of collimation levelling technique for both single stations and multiple stations, so single locations, multiple locations, how we book intermediate stations, and go over some guided practice booking level readings and performing level calculations. Levelling is used to find heights, that's all it really does, but that is so useful and it is an integral part of any construction site. You will always see a level on site, you will always see people using them. As student and as graduate engineers, if you are ever on site, you will almost certainly be carrying out levelling exercises. So it's really good to get the practice in now, know what you're doing now. This course should prepare you for a summer job, for example, in construction. If you wanted to apply for a summer job in construction, start looking now is one thing. And you'll probably be doing various surveying techniques, so levelling, control surveys, mapping, setting out. This whole course is designed to give you what you need in order to get one of those jobs, really. It makes you really employable by the construction companies. So we use levelling to find contours, which are lines of equal elevation, spot heights, and that could be heights of existing structures or heights of ground where you want to create structures. And it covers also bathymetry, so water depth, depth of rivers, depth of coastal areas. Wide applications, anything to do with construction, so buildings, drainage, water supply, canals, roads, railways, etc. There are some pictures of people surveying. We are using the optical level. We have optical levels at this university. There are other sorts of levels. A level is just a device that you can set up to be purely horizontal. So on the level there are small bubbles and they allow you to align that level so that it is perfectly flat and it views across a horizontal plane. It's an optical level because it's a telescope and we use our eyes, so we're using optics to make sure it's level. You can get laser levels which use laser sights, laser dots, and gauge whether the device is level using that. We need a levelling staff to measure vertical distances. When you look through the level, there is a target and crosshairs. So you look through the level, you will see this. You will see a horizontal crosshair, vertical crosshair. You want to read the reading that is intercepted by the horizontal crosshair. If we look at this little example, if the crosshair was intercepting the staff at this location, it's 2 meters 923 millimeters. How do I know that? Each of these coloured blocks is 1 centimeter. So from 2.9 meters, which is this location, to 3 meters, which is this location, we've got 10 bi-coloured blocks. We've got 1 centimeter, 2 centimeter, 3, 4, 5, 6, 7, 8, 9, 10. Each of those centimetre blocks can be visually subdivided into millimetres. So this crosshair is crossing approximately 3 millimetres up from 2.92, so the reading is 2.923. One thing to note, it's very, very common for people to read the wrong crosshair. So we have a central crosshair, which is where all your readings should be taken, but note that there are crosshairs above and below, and they are used for different surveying techniques for distance calculations. We're not going to be using the upper and the lower crosshairs. We are only interested in the central crosshair. The level is also needed, which is defined in the horizontal plane. Looks like this. It's just a telescope on bearings that can be adjusted. So this whole device swivels around, and there's a telescope in this long section here which allows us to look through and view this image. The tripod is 3 legs, and we use this to mount the level. It's 3 legs because it's more stable on an even ground. We also need a known datum. We can't do levelling unless we know the height of at least one point. This is normally noted by a benchmark, and the benchmark can be either an official benchmark or an ordinary benchmark that is defined by British Geological Survey, or we could define our own temporary benchmark. The image here is an ordinary benchmark that is defined by the British Geological Survey. So it is a bronze pin embedded into concrete, which may be in a pavement, for example. By making sure that the benchmark cannot move, we can have confidence that the height of that benchmark is not going to change from year to year, so it can always be used as a reference datum. So the levelling procedure is as follows. The first step is to set up the instrument in the midpoint between the point where the height is known and the point where the height is not known. We use the term reduced level, RL, to define a ground level or an object level. So in this case, our known level is the ground here, our reduced level is here. Our unknown point is up here. In order to find what the ground level is here, we put the level set up in between, as close to the midpoint as possible. We then need to create the level plane so that we have a height of collimation, which is a horizontal plane which is entirely flat. We read the staff at the point where the reduced level or height is known. This is called a back sight. It's called a back sight because the direction of levelling is, in this case, going from left to right. So we're looking back towards the known level, so it becomes a back sight. That allows us to calculate the height of collimation by adding the reading of the staff, where the back sight is read, to the reduced level of the known point. So the ground level here, which is normally given as the height above sea level, mean sea level is MSL, reduced level is the height above sea level, the back sight is the height above the reduced level. So our height of collimation is given by HC is equal to reduced level plus back sight. You then look forward to your unknown point to place the staff on the unknown point, look through the level, and you can read the foresight. The foresight because it's in the forward direction. We can then calculate the level of the unknown point by subtracting the foresight reading from the height of collimation. So a quick summary, a back sight is a staff reading on a point of known elevation. It's normally the back point in the survey. Height of collimation is the elevation of the line of sight through the level. That's this horizontal plane here. The foresight is a forward reading. An intermediate sight is any reading that is taken between the back sight and the foresight. And turning point is shown on the next slide. Because sometimes on very steep ground or very long distances, it's not possible to set up the level in one location and see from your known point to your unknown point. So we've got the level set up, the height of collimation. It's too high for point A and it's too low for point B. So we have to use turning points and multiple setups. In this case, we've got our level, height of collimation, reading a back sight at A, a foresight at a turning point, TP1. We then move the level, and we take a back sight to TP1 and a foresight to B. Intermediate points are any points taken in between the back sight and foresight. So if you're going to take another reading in the middle, somewhere here, you would take your back sight first, then the intermediate sight, and the last reading you take at that location is the foresight. Here is a site that has been marked for development. We have 2 known points. We know A is 89.562 metres above sea level. We know that point G is 88.3 metres above sea level. So we do know that G is lower than A, but we don't know what the profile is in between the land, and what we want to work out is where the high points, where the low points are. So a simple way to do that is to take a quick grid of points. We can use a level to do this. The first thing you always do with a level is go back to your known point so that you have a known datum. So we take a backside to A, and the reading on the staff is 2.341. We'll then measure a point below the path. We'll call this point B, and that reading is 3.796. We'll take another intermediate sight reading to C at 0.409. And another reading at D, 2.220. These levels can only really work with a distance of 25 metres sight, with a great deal of accuracy. So we now have to use D as a turning point. Move the level over the other side, and now we take a backside to D. 3.431. We'll take another intermediate sight at E, 4.078, and another intermediate sight at F, 0.953. All that's left now is to take a final 4-sight reading to G, and we get a reading of 4.806. So that gives us all of our readings. I'll just complete labelling the points as well. So in the notes section, I'm just using this to note which location each of these readings is at. I can also transfer over the reduced level that I know at the beginning, because we started off with this level, so we assume this was a true reading. 562. So how do we compute the rest of the ground levels of these points? Well, we need to work out the height of collimation. Take a minute, have a look in your notes and see if you can work out what the height of collimation of the very first level setup point, this level point, is here. Well, remember that the height of collimation is the height of the actual telescope that you look through when you use the level. So we can work that out by adding the reduced level on the ground to the backside. So I'm going to add 89.562 to 2.341. Gives us 91.903, so well done if you got that. I can then use this height of collimation. I know the height of this level, so if I know the height of viewing plane of this level, I can use that to work out the reduced levels of B, C and D, just by taking away the intermediate sight and the 4-sight readings. So the reduced level of B is going to be 91.903 minus 0.409, giving 91.494. Likewise for the next one, I've got 91.903 minus 3.796 to give the reduced level of C. So now find the reduced level of D, following the same logic. So we follow the same logic. We've got the height of collimation, 91.903 minus the 4-sight, 2.220. And the reduced level, well done if you got this right, is 89.683. D is special because it's a turning point. The reason we've got a turning point here is because the distance between A and G is too large to just do one levelling survey, so we have to do half the area in one position, half the area in the other. And to transition that datum, we're going to use D. So we move the level over. We've taken a backside here. That means we've now got a new height of collimation. So the height of collimation, as before, is equal to the reduced level plus the backside, which you've just worked out. So 89.683 plus 3.431 to give 93.114. We can now use this new height of collimation to compute the remaining reduced levels. So 93.114 minus 4.078 gives 89.036. 93.114 minus 0.953 will give 92.161. And again, height of collimation 93.114 minus 4.806 to give the final reduced level of 88.308. Well, for levelling checks and list closures, we've got some simple formulae to remember, and you should be remembering these, knowing these. The first one is the arithmetic check. For this, you just sum all your back sites and all your foresights, and you compare it to your last reduced level minus your initial reduced level. The second check is only used when you have intermediate sites. It is the sum of the intermediate sites, the sum of the foresights, plus the sum of the reduced levels except the first reduced level, and that should be equal to each height of collimation multiplied by the number of times that height of collimation is applied in calculations. If the left hand and right hand side of these equations doesn't match, then there's either an error in your staff readings or your calculations. So you need to go back and check. For misclosure and booking adjustment, we work out our total error, which is the measured value minus the true value. Compare that to the acceptable error, which will vary for each survey, and the equation for that is equal to p times root n, where p is a constant that depends on the required accuracy. We'll normally be using either precise or normal precision, and n is the circuit length in kilometres, and if it's unknown, then we'll just use the number of instrument positions that we have. In this case, we've got 2 instrument positions because the instrument was moved once. As long as the total error is less than the acceptable error, then we can accept the survey. If not, it is deemed outside the limits of what is acceptable and should be repeated. This error is then distributed according to each instrument position. So I'll go through that now for the example we've just covered. These were our results, and I've summed up each column at the bottom. So the first arithmetic check is the sum of the back sites minus the sum of the foresights should be equal to the last reduced level minus the initial reduced level. Put those numbers in there, and we find that both sides is equal to minus 1.254. So the first arithmetic check works out fine. The second one, we add the intermediate sites, add the foresights, add the reduced levels, except the first one, and that should be equal to each height of collimation multiplied by the number of times it's used to do a calculation. So this height of collimation was used to work at the reduced level of this point, and this point. And this height of collimation was used to work at the height of this point, and this point, and this point. So 3 times each. The first height of collimation by 3, add that to the second height of collimation by 3. Once again, we end up with that okay. Both sides equal to a number. It doesn't actually matter what these numbers are. What matters is that the numbers are the same. So we're okay. The misclosure check is simply the reduced level that was obtained minus the reduced level that it should have been. Because we know the ground level at G is 88.3, and our calculations, our levelling exercise, it came up with 88.308. We take away 88.3 from 88.308, and that's 8 millimetres. The acceptable error for a precise survey in this case is p root n, so we've got 6 because it's a precise survey, multiplied by root 2 because we've got 2 instrument positions. So the acceptable error for this survey was 8.4 millimetres. So we are only just within what is an acceptable error. The correction is the total error divided by n divided by the number of instrument positions, number of level positions. So n is 2, the correction is 0.004 metres. We then apply the first correction of 4 millimetres to the locations that are measured using the first height of formation, and the second one to the second level location, 0.008. So we've added half of that correction to the first 3 points measured and the full correction to the second 3 points measured. We can then work out the reduced levels, which are the ground levels of the rest of the points, by subtracting the correction from the reduced level. You can see from the very last point that if we take away 8 millimetres from this reading, we get to the true reduced level. Therefore, we can be confident that if we apply this correction, we get a good, pretty close approximation of that ground level, probably to within a couple of millimetres. So, another example. If we need to take an inverted reading, for example, a bridge culvert, we can use the staff upside down on the inverted point to take the reading. You have to book the staff reading as negative in this instance. So here you can see we've got a ground level B on the right hand side, and we're taking an invert reading, looking at the underside of this bridge structure as A. So the level is turned upside down, the bottom of the staff is placed on the top of the bridge, and we book that reading as negative. In this case, we're looking at the underside of a bridge. We've only got one location here, one levelling location here. Let's put them in. Okay. In this example, we're looking at measuring how high the invert point of these bridges. So we're putting the level in the middle of the road in one location. We've got a reduced level, a known level on one side of the carriageway and a known level on the other side of the carriageway. We're going to measure in between the two. So the level looks over to A, makes a reading of 2.104. B, we get a reading of 2.589. C, a reading of 2.426, and D, a reading of 1.937. There are no turning points in this example, this is one level setup. Have a think, pause the video and have a think about how you would book those readings, and start the video when you have done that. Okay, it should look something like this. You could do the other way around, but since I've labelled them A, B, C, D, I think starting at A makes sense. So the level backside to A is 2.104. The reading to B is 2.589, but we need to book it as negative because it's a bridge culvert. Same with point C. And then the foresight to the last point, 1.937. I've also put my known reduced levels into the table. I know that the reduced level here is 10.560 and the reduced level at the far end is 10.728. The first step is then to work out the height of collimation and the reduced levels will follow on from there. So again, have a pause of the video and see if you can work out what those values would be. So those values should be as follows. I've lost my reduced level. The height of elevation should be 12.664. And then we get that all. We get 12.664 by adding 10.56 to 2.104. To get the reduced levels, we need to then subtract the intermediate sites and the foresights. So we have a reduced level of 10.56 on this side of the carriageway. The invert of the bridge up here is 15.253, up here it's 15.090, and the ground level back here is 10.727. The first arithmetic check is the sum of the back sites minus the sum of the foresights. It should be equal to last reduced level minus initial reduced level. We've only got one backside and foresight here, it doesn't matter. If you do that yourself, you'll find out that they do match 0.167 on both sides. So the first arithmetic check has worked out okay. We can also perform the second arithmetic check. So all the intermediate sites, all the foresights and reduced levels, except the first reduced level, so in this case except 10.56, should be equal to the sum of each header collimation times the number of applications, the number of times that it's used. So the sum of the intermediate sites is the sum of these two values plus the foresight plus the reduced levels except the first one is equal to the height of collimation multiplied by 3. It's multiplied by 3 because the height of collimation is used to work out this reduced level on the second line, this one and this one. This first reduced level was given already. This is a known value. Both those sides equal the same number. Again, the number doesn't matter. What matters is that both sides are the same. Therefore, both those arithmetic checks have checked out okay. For the disclosure, we compare the final reduced level that was measured to the reduced level that we know to be true, and that gives us a negative 1 millimetre value. The required accuracy is 6 millimetres, so we are well within accuracy. And the correction, because we only have one station, will be 1 millimetre for all of those points. So we've added on 1 millimetre to each of these reduced levels to give us the final reduced levels there. So that's the end of the examples. The next thing for you to do is to complete exercise sheet 1 to have some practice doing level booking and calculations.